Hello everyone and welcome back to Calculus. I'm ready for my next video and hopefully you will find it helpful to you. So what we're going to talk about in this section, this is section 1.3, is what we call infinite limits. And it's related to another topic that you might have already seen in a pre-calc class called asymptotes, and we'll talk about both of those today. So in order to start, let's zoom in on this top section here, right there. And what I would like for you all to do is to plot, hang on, let me fix this. That needs to be a plus, and this needs to be a plus. Okay. There we go. All right, so let's get that right again. Okay, so what I would like for you all to do is graph the function that I've given you here, f of x equals 1 over x plus 1. So you will probably need to pause the video and you might want to make out a table. You'll notice I have a table on the right-hand side here, which is related to the question, but you'll notice it doesn't have a lot of values on it. It's only got values right around -1, which you can probably figure out that there's something odd going on there. So you'll need to plot other values as well. So what I would like for you all to do is pause the video, fill out a table to plot the values, including the ones that I've got to the right, but also including other ones. All right, and when you're done with that, we'll be back and we'll go ahead and continue. All right, I guess you all are back now, so let's plot out some values. I'll try and just work through these, except for the ones on the table. We'll fill that out. But first of all, let's look at what happens if I plug in 0 for x. If I plug in 0 for x, I get f of x is 1, so that's this point right here. I'm going to try and put these in blue. If I plug in 1 for x, I get a half for f of x, which is that point right there. If I plug in 2, I get a third, which is right about here. If I plug in 3, I get a fourth, which is right about here. So we get points going like that. On the other side, let's plug in -2. If I plug in -2, I should get -1, which is right over here. Let me make these a little bit bigger so we'll be able to see them later. Okay. And if I plug in -3, I get -3 plus 1 is -2, so 1 over -2, which is -1/2, which is right about there. And if I plug in -3, I get, wait, hang on. Sorry, that was -3. If I, -3 is -1/2. If I plug in -4, I get -1/3, which is right about here. Okay. So those points shouldn't be too hard for you to find. They're fractions, but you should still get values that make sense. You'll notice the values around -1 I have separated out here, so hopefully you've figured those out. The first one we'll talk about is -1 itself. If I plug that in, I get 1 over 0, which by this point we all know is undefined. Sorry about that. Let's scoot this over. Undefined. I know I have to zoom in and out, but my writing won't be legible if I try and write small on this. So that's what we get there. Now, if we fill in these others, we get things that are a little bit different. So let's go ahead and try that. Let's start with -1.5. If I plug in -1.5 into x, I get -0.5 on the bottom. 1 over -0.5 winds up being -2. If I do the same thing for 1.1, I get 1 over, or negative 1.1, I get 1 over negative 0.1, which gives me negative 10. And if I get even closer in there to negative 1.01, you'll see I get negative 100. If you plug in the ones down below, you'll see that you get similar answers, except these will all be positive. Hopefully you filled it out already, so here we go, 100, 10, and 2. Now you'll see that some of these are easier to plot on our graph than others. The negative 2, where we're at negative negative 1.5, that's not so hard to plot. We could plot that right here. But by the time you get to negative 1.1, you're already at negative 10, which is off the graph. So you can see what's happening here. Let's do this in red, sorry. See what's happening here is this thing starts going down really fast when we get towards negative 1. On the other side, if we plug in negative 0.5, we get 2, which is right here, and we draw this graph, we see the same thing happening, except this one goes up instead of down. So we get this graph that looks like it's in two pieces, two curves that sort of face each other. And anytime we have, or a lot of times we have denominators in graphs, we'll get this kind of weird two-piece graph like this. One time we won't is, well, we've seen sometimes that we didn't in the first section, but you'll notice that these two graphs are both, hang on, let me get up here, are both approaching this line here. I'm going to put it in dotted. Hopefully this looks good when I'm done, because this will be what you have for your PDF. There we go. So you get these both sides of the graph approaching that vertical line at x equals negative 1. This thing right here is what we call an asymptote. Hang on, blue. And more particularly, this is what we call a vertical asymptote. We do have horizontal asymptotes as well, but we won't get them till later. Vertical asymptote. Vertical asymptote. Okay, so that is what we're talking about, part of what we're talking about today. So you'll notice here that either side of this graph does some weird things when you approach negative 1. And it doesn't do the same thing. You'll see the function value keeps getting higher and higher on as we go toward negative 1 from the right, and as we go toward negative 1 from the left, it keeps getting lower and lower. And in fact, if you get close enough, you can make that get as big as you like or as small as you like. So obviously this throws a wrench into what we've been dealing with for our limits so far. But not in all cases. So just to show you that even functions like this can have limits that are easy to calculate, I would like you to look at these first two and work on those on your own. Go ahead and pause the video and find those out. Those shouldn't be anything new to you. In fact, they should be stuff that we could have done in a previous section. So go ahead and pause the video. I'll be right back. Okay, so if we plug 2, sorry, I need to have both things visible there. Okay, if we have plug in 2, we get 1 over 2 plus 1, which is 1/3. And if I plug in -3, I get 1 over -2, which is -1/2. And plugging those in and getting values, remember, if we have a polynomial over another polynomial, we're allowed to do that when we're finding a limit. So it's easy enough to do there. I have to edit these ones now, don't I? Because I changed that function before I started. Okay, so let's edit those out. So the point that was the issue here, I changed the function because I wanted to make it a different one than you had in the book. So here we want to look at x going to -1, x going to -1 from the right, and x going to -1 from the left. Okay, so these are the points where we have an issue, where things don't work out the way we've dealt with before. Now, in order to talk about the limit as x goes to -1, at first we'll have to talk about these other two limits, the limit as x goes to -1 from the right and the limit as x goes to -1 from the left. So those are, in order to talk about the other one, we'll have to talk about those first, because as you can see from the graph, what happens as we go toward -1 from the right, from this direction, is different from what happens as we go toward -1 from this direction, right? You can see that where the function is going is different in both directions. So we should have different answers here. Now, one way to answer both of these questions would be to say that these limits don't exist. And that is a valid answer here. It's not illegal or anything to say these limits don't exist. But we can actually say a little bit more if we're willing to phrase it in a different way. So if we go toward -1 from the right, you see that's where our values are getting bigger and bigger as we go up toward this area. If we go in toward the right, we go up toward that area, and that gives us bigger and bigger values. And they get as big as we like, so we say that this limit is infinity. And you'll notice I'm putting a plus on that. That probably gives you a hint to what the next one is. If we go in from the left, we keep getting smaller and smaller, bigger and bigger negative values, in other words. And so our limit here, then we would say, is -infinity. So one thing I do want to point out here, oops. It is still legal to say these limits don't exist. Even though we have another term for it now, it's still okay to say limits of infinity or -infinity don't exist because it's okay, but it doesn't tell us everything we might want to know. So typically we say the limit equals plus or minus infinity instead of doesn't exist. Now this other limit, you'll see we still have two different values as we approach from two different sides. So really the only thing we can do here is say that this doesn't exist. That's not how you spell exist, is it? There we go. That's better. All right. So, this one, there's nothing we can say about it other than it doesn't exist. But the other two, the ones approaching from one side or the other, we can say that those are plus or minus infinity. Okay, so that is what we mean by infinite limits here. Okay, now I've already talked about that this is related to the concept of a vertical asymptote. You saw here we had this vertical line x equals -1 here, right? I may have said y equals -1, but if I did, I misspoke. Let me go ahead and put it in here. So this line is x equals -1. That is our vertical asymptote. Now, a vertical asymptote, we can actually describe this in terms of limits. A vertical asymptote is a vertical line that the function approaches but doesn't touch, and wherever a function has a limit of plus or minus infinity, it has a vertical asymptote. So essentially, if you're looking for vertical asymptotes, you're looking for limits that are equal to plus or minus infinity. Limits that don't exist because the values get really, really high, really fast, or really, really low, really, really big negative values really fast. So that's what we're talking about when we have vertical asymptotes. Now, how do you find those? So here, essentially the idea is to find these. You would want to find all places where the limit is, I'll leave some spaces to write plus or minus infinity there in a second. So you will have to first find where are the only places that we could have a limit of plus or minus infinity. Actually, let me write this in here. So where are the only places we could have a limit of plus or minus infinity? Pause it for a second and think, see if you can answer that. All right, the answer here, the only places we can have a limit of plus or minus infinity are where the denominator is 0. Now, that's not, every time the denominator is 0, we aren't guaranteed a vertical asymptote. And the reason that is if we actually have a limit, and you'll remember we had some examples where we had a denominator of 0, but the limit still existed, those aren't vertical asymptotes. There's just a little gap, a little hole in the graph. So what we have to do there is we essentially have to, if the numerator cancels the 0 in the denominator, we don't have a vertical asymptote at that place. There we go. Okay, so that is what you would want to do to find vertical asymptotes. You want to find all the places where the limit is plus or minus infinity. So essentially, what you have to do here, let me sort of write out a couple, not write out steps, but sort of explain to you what you need to do. Here, what you would have to do is, if you have a function like this and you want to find where the vertical asymptotes are, you need to find where the bottom is 0, right? You need to find where the denominator is 0. So in order to do that, you have to factor that and set it equal to 0. But you also have to factor the numerator, and if things cancel, if it cancels with the top, essentially it doesn't count as a vertical asymptote. There we go. So that's the idea. That's what you need to do here. So what I would like for you all to do is pause and work on this first one. Work on the first one to see if, let me fix this. This doesn't look quite like I would like it to. Look at this first one. So in other words, factor it, figure out where you have vertical asymptotes and where you don't. Okay. So, actually, let me fix that too, because I highlighted it, but just so you can see when you look at this later, if you just look at the PDF, set the bottom equal to 0. Okay. So, go ahead and pause the video and try and find the vertical asymptotes of this first function. And when you're done, you can unpause the video. Okay, if you're back, let's take a look. So, we're back to some algebra here. We have to factor these things. So you'll notice we have, if we look at what we have on top, let me factor these, let me set this up here so we can be ready to factor. Okay, so if you look at what we have on top, we have x squared as the first thing in this. So what that means is if we factor this, both of the factors have to start with an x, right? This is just a reminder of some techniques from algebra that you might not remember. Same thing in the bottom. We should have two x's here as well, x and x. Now, the second thing you should notice about the top, we have a minus in the middle and a plus on the end. The plus on the end means we need two things to multiply to give us 6, and the minus in the middle is those same two things need to add up to -5. So if you have minus in the middle and plus on the end, both of these things have to be minuses. And if you have a minus, so here we had a minus in the middle, a plus on the end. Here we have a plus in the middle, a minus on the end. The plus in the middle doesn't really matter, but the minus on the end tells us one of these is a plus, one is a minus. Okay. Now, on top we need things that multiply to give us 6 and add to give us -5. So what we can do there, things that multiply to give us 6, 2 and 3 is an example, and if we add those we get 5, so 2 and 3 is what we need here. On the bottom, if we look at 12, we want things that multiply to give us -12, but if we add them together we get +1. So multiplying to give us -12, there are lots of options, right? 6 and 2, 1 and 12, 3 and 4. But we want their difference to be 1. So what that would be is I would want 3 and 4 because they're 1 apart from each other. And the one I want bigger is the one that makes their sum a positive. So I want a 4, a 4 here and a 3 here. And then that is the fully factored version of this. Okay, now, if we look at that, do we see anything cancels? Well, the answer is yes. We see that that x minus 3 cancels on the top and the bottom. And remember, if something cancels, we don't get a vertical asymptote. So here are only, let me put part of this in red, our only vertical asymptote then is whatever is left on the bottom that gives us 0. Well, that's x plus 4 equals 0, or if we rearrange that, x equals minus 4. That is our only vertical asymptote here. So that's our answer. Hopefully that makes sense to everybody. And again, anytime something doesn't make sense, feel free to contact me and let me know, and I'm happy to help. Okay, so let's do the same thing down here. And again, I got to zoom in so I write this so it's legible. Okay, let me even set this up a little bit for you. Not too much, but just a little bit. Okay, so what I would like for you to do now is do the same thing for this one. Find the vertical asymptotes for this second one. So factor top and bottom first, and then proceed from there. So go ahead and pause the video and finish that up. Okay, if we did this right, well, is anything easy? Well, you'll notice that the top is the same as the top we had before. Actually, let's undo that. Let's make that yellow. The top is the same as the top we had before, so we don't even have to factor the top anymore. This is x minus 2, x minus 3 still. So I'm good on that. Don't have to mess with that anymore. The bottom, on the other hand, is different. So now I want things that, so you'll notice here, I have 2 pluses. That means the numbers in the signs in the middle here both have to be positive. I want things that multiply to give me 12, add to give me 7. Well, my answer there is 3 and 4. 3 times 4 is 12. 3 plus 4 is 7. And if you try anything else, 12 and 1, they don't add up to 7. Oops, sorry. 12 and 1, is this right? Nope. There we go. Where are we? I must have shut this down. Hang on. Let me go back and find the right one here. Where are you all? There we go. Okay. Sorry about that. You touch the screen and it hits an X and the whole world blows up. Okay. So here we go. There is a... so we get this factored version now. So again, we want to set the bottom equal to 0, but if something cancels with the top, it doesn't give a vertical asymptote. If we look at these two, do we see anything that cancels? Your first instinct might be, well, I see a 3 on the top and a 3 on the bottom, but notice that these are different. They would have to be the entire same thing multiplied in to be able to cancel, so they're different, so they don't cancel. So we can say no canceling here. And if we say no canceling, that means that we just set the bottom equal to 0. So we set the denominator equal to 0. And if we do that, it's x plus 3 times x plus 4. And if you want to set a product equal to 0, you have to remember that means one of the two things has to be equal to 0. So that means we get 2 results here. We get one that is x plus 3 equals 0. And the other one is x plus 4 equals 0. So each of these is going to give us a vertical asymptote. This will give us a vertical asymptote. And our first one is going to be x equals minus 3. Our second one will be x equals minus 4. So we get 2 vertical asymptotes there. All right. So hopefully that made sense. That's pretty much chapter 3, or section 3 of chapter 1. Hang on, let me see if I can draw you something here. It can be a little bit tough to draw on this thing, so let me see if I can manage it. That's working out okay. I'm a little bit more used to the chalkboard, but whatever. We can do it anyway. I need green there. There we go. And okay, and let's zoom in a little bit. And what does a disgustingly wealthy penguin have in his hand but a martini? Alright. And got to put the olive in there. Unfortunately, we have the right color on this thing for that. And let's see, let's color this in a little bit. I'm doing this, but you can certainly stop the video now. This will be on your PDF and, of course, on the final. But reproduce the penguin for 100% of the grade. Cross-hatching seems to be the way to go on this thing. But maybe not. Maybe I'll do this. Okay, and yeah, red bow tie, I think that'll do. There we go, and so there's our penguin. Actually, now that I see it, I don't like the cross-hatching, but too late to fix it. Alright, so there's your penguin for the day, and that's the end of the video. Please let me know if you need anything else. And I will talk to you again soon, and I'll be continually posting these videos. Please let me know if you have any questions, and we'll talk soon.